When architects designed the El Castillo Pyramid at Chichen Itza, they were executing strict geometric principles in physical space. But if we strip away the limestone and mortar from this ancient structure, we are left with a pure mathematical skeleton. Three-dimensional geometry analyzes how simple two-dimensional planes combine and fold to dictate the architecture of complex solids. To understand these structures, we will define the properties of polyhedrons, apply Euler's structural equation, and categorize the Platonic solids. We will then use these flat-faced shapes, combined with the concept of mathematical limits, to calculate the volume of a perfectly smooth sphere. Mastering these rigid geometric rules provides the framework required to measure the continuous, curved reality of the physical world. The fundamental building block of 3D space is the dihedral angle, formed when two half-planes intersect along a common edge. When four or more of these flat plane regions intersect to entirely bound a solid, they create a polyhedron. Polyhedrons have three components: flat faces, intersecting edges, and terminating vertices. In a convex polyhedron, a plane containing any face leaves the solid entirely on one side. A concave polyhedron breaks this rule. A diagonal connecting internal vertices passes through the empty space outside. Determining whether a shape is convex or concave is a critical distinction, as it dictates which mathematical theorems we can apply to calculate its properties. In the 18th century, Leonhard Euler discovered that convex polyhedrons are governed by a specific relationship between their components. Euler's equation states that for any convex polyhedron, vertices plus faces equals edges plus 2. A tetrahedron has 4 vertices and 4 faces, equaling its 6 edges plus 2. Similarly, a square pyramid's 5 vertices and 5 faces equal its 8 edges plus 2. This rule applies specifically to polyhedrons. Shapes with curved surfaces, like cylinders and cones, do not follow this equation because their boundaries do not lie in flat planes. For solids bounded by polygons, Euler's equation proves that 3D geometry is defined by an exact mathematical ratio. We can apply even stricter requirements to these solids. A regular polyhedron is a convex solid built entirely of congruent regular polygons. While we have an infinite number of regular polygons to choose from, geometry only permits 5 specific configurations that satisfy this definition. These are the regular tetrahedron, hexahedron, or cube, and regular octahedron, constructed from congruent equilateral triangles or squares. The final two are the regular dodecahedron, made of 12 pentagons, and the regular icosahedron, consisting of 20 equilateral triangles. The requirement for absolute congruence across every face acts as a severe structural filter, narrowing infinite possibilities down to just these 5 anchors. Transitioning from rigid polygons to round geometry requires a shift in terminology. While half of a 2-dimensional circle is a semicircle, half of a 3-dimensional sphere is a hemisphere. To find the volume of a perfectly smooth sphere, we treat it as the theoretical limit of a flat-faced inscribed polyhedron. We separate the inscribed shape into a number of congruent pyramids, with each vertex meeting at the sphere's center. Increasing the faces toward the limit of infinity, the bases of these pyramids multiply and shrink, mapping to the sphere's inner wall. At this limit, the flat altitude of each internal pyramid functionally becomes the curved radius of the sphere itself. The sphere's volume is therefore defined as the limit of the sum of these infinitely small internal pyramid volumes. This concept of limits provides the necessary bridge, allowing us to apply simple, rigid geometric rules to calculate the volume of smooth, curved surfaces. In 3D space, spheres can be tangent to planes or other spheres, touching at exactly one precise point. We can also generate these shapes through rotation, creating what are known as solids of revolution. By revolving a 2-dimensional region around a central axis, we can map out a 3-dimensional volume. When we spin a flat semicircle around its central vertical axis, its path generates a perfectly smooth, solid sphere. If the axis of revolution is moved outside the original 2-dimensional shape, the resulting solid takes on a different geometry. Rotating a region around an external axis creates a hollow-centered solid called a torus. While we can define the torus here, calculating its volume requires the more advanced methods of calculus. We have traced the progression from the simple intersection of planes to the construction of complex curved solids. Euler's equation provides a method to verify the structural logic of three-dimensional polyhedrons. By applying the concept of limits, we use the properties of these flat-faced shapes to accurately calculate the volume of smooth curves. This progression marks the boundary between static geometric definitions and the continuous calculations utilized in calculus. These mathematical rules and boundaries provide the framework necessary to calculate the dimensions of the most complex structures we encounter.